I would like to recall the four main material categories: metal alloys, polymers, ceramics and composites. In this session I will explain a bit more on the properties and try to relate them to the material composition. If we first look at metals, I can mention a number of advantages. First, its isotropic behavior. Isotropy means that the material properties are the same in all directions. This isotropy stems from the microstructure of the metal. It is a polycrystalline material with random orientation of the crystals. Second, metals can be strengthened easily. Alloying elements can be dissolved in the molten metal, thereby the properties can be influenced. Metals and their alloys can be easily processed by melting and casting, but also by plastic deformation. By applying a high force, the material yields and changes its shape. Finally, metals are often reasonably priced because they are produced in large quantities. In this slide you see 7 metal alloys and their properties: 2 steel alloys, 3 aluminum alloys and 2 titanium alloys. From the table one can see that the density and E modulus are more or less constant within the same metal group, but other properties differ significantly. The 3 aluminum alloys show nicely the effect of alloying. Pure aluminum has low yield and ultimate strength, but a high failure strain. When aluminum is alloyed, the strength values increase and the failure strain reduces. The 7000 alloy is about the strongest aluminum alloy, having a more than 6 times higher ultimate strength than the pure aluminum. At the same time, the failure strain, representative for its ductility, is reduced to nearly 25%. Similar relations can be seen for the other metal alloys. For aerospace applications, not the absolute material properties are important, but the specific properties. These are properties expressed as performance over weight ratios. Which ratio to choose depends on the load situation. For tension load cases you need a different ratio than for compressive loads. In this slide you can see the specific properties for tension. All stiffness and strength values are divided by the density of the material. If you compare these values with the absolute values, you see that the ranking between the different alloys has changed. Aluminum alloys perform much better now because of their low density, and steel alloys are hampered by their high density. Next material group is the polymers. As mentioned before, the polymers are no structural materials themselves, but are an important ingredient for composites and therefore interesting. Polymers are also isotropic, have good processability, are available in a large variety and have low costs due to large production volumes. Thermoplastic polymers have also plastic forming capabilities when heated and can be melted. These processes are reversible. Thermoset polymers don't have plastic flow and cannot be melted or solidified. The figure shows the injection molding process used for thermoplastic polymers. The process temperature is high and the applied pressure assures proper filling of the mold cavity and the cycle time is short. The plot in this figure indicates the E modulus of a thermoplastic polymer. This illustrates that the material properties are temperature dependent, but also time, strain rate and the environment influence the material properties. At room temperature, the thermoplastic polymer is a solid. By increasing the temperature, the stiffness drops to a much lower level. This happens at the glass transition temperature, Tg. At this second level, the material behaves like an elastomer, a rubber. When deformed at this temperature, followed by cooling down, the enforced shape is preserved. A further increase in temperature will ultimately melt the thermoplastic polymer, although the viscosity remains rather high. A thermoset polymer does not have a rubbery state, nor does it melt. When the temperature becomes too high, it evaporates or decomposes.